So again, today we're gonna do tangents, and then we're gonna use these formulas to verify some identities, okay? So let's jump into that. Up here, I'll leave it up here. These are the formulas we just did in the last period, and we derived them, okay? So we'll do the same thing with tangent. We'll derive what that looks like, and then we'll start using it. So let's put here. So we can derive our tangent sum formula by using our identity and sum formulas for sine and cosine. So I don't have to draw that picture at the very beginning of yesterday, like drawing a unit circle and subtracting it and go from there using distance formula. I can use some of these identities to get the tangent a lot faster. So let's start with tangent of alpha plus beta, okay? What would that be equivalent to? So let's use the identity of sine and cosine, because we know that's what tangent's equivalent to. Okay, so I'll break it apart that way. And the good news is we know what those formulas are. They're right up here. Okay, so that's why I wanted to keep it up here so we can use it as a reference. So let me go ahead and substitute that. Bless you. Minus. Okay, so again, what I did, I broke this up into its equivalent, sine and cosine. And then because we know what these formulas are, which we derived from yesterday, I went ahead and substitute those in. So now I'm gonna go ahead and simplify that and see what is tangent of alpha plus beta truly equal to, okay? So we clear so far in the process of what we're doing? Here we go, okay. Now, I'm gonna do something a little different here. To simplify this, I'm going to multiply the numerator and denominator by 1 over cosine of alpha, cosine of beta, okay? The reason why I'm doing that is because I want my answer to have tangents in it when I'm done with it. And this is one way I could do that. So let me put this in a different color here. So 1 over cosine of alpha, cosine of beta, okay? So I'm going to multiply top and bottom by that. Because I'm multiplying by the same thing, I'm not really changing the values of these equations. Okay? So what I just wrote in blue, this is me multiplying top and bottom by that. Okay? I'm going to put on the next whiteboard. I don't want to try and squeeze it below here. Plus, not a lot of people can see if I do right below there. So let's see what this looks like. So in the numerator, okay, we're going to get the following. So sine of alpha, cosine of beta, over cosine of alpha, cosine of beta, plus cosine of alpha, sine of beta, over cosine of alpha, cosine of beta. Okay, so that's my numerator. That's just me taking that blue fraction, multiplying to both terms there. Denominator, same thing. You know, when you're doing proofs with trig, it's always going to look more like complicated until you start whittling things down, like using identities, using some algebraic properties. Then it starts getting a little bit easier to work with. But in the beginning, it's a little daunting. There we go. I will say, like, the proofs I did in grad school, so you would do like 2 full pages of just this paragraph proof of everything you do. professor looks at it and goes, there's a flaw at the very beginning. You're like, well, that's 6 hours wasted. I gotta go back to the drawing board and try it again. It's brutal. But at least I think for like trig and algebra, like those proofs, it's nice because you actually have things to kind of work with. When you get higher, up with some of the other math courses, it's really tricky stuff. Now I can see some things canceling. I'm gonna do that with this blue marker. So I can see these guys are gone, those are gone. Let's see those guys, and hey, even those guys are gone. And I think that's it. Yeah, that's all it kind of cancels out. So there's a lot there that did reduce pretty nicely. So what's this gonna be now? It's gonna be sine of alpha, cosine of alpha, sine of beta, cosine of beta, and that's just a 1 now. And unfortunately nothing reduced in that other fraction over there. We got one final step, and then we got our formula. So if you notice in the numerator, that is tangent, right? Twice. This is tangent for alpha. This will become tangent for beta. So that's pretty cool. Let's rewrite that. So this is tangent of alpha, tangent of beta. And then on the very bottom, notice that I have 2 tangents here. I mean, they're combined in one fraction, but I have a tangent of alpha for this part of the fraction, and a tangent of beta for that part of the fraction. So this becomes 1 minus tangent of alpha times tangent of beta. And there we go. So let me, this is gonna be backwards. That's okay. So that's what tangent of alpha plus beta is equal to. So this is our next formula that we'll be using. Okay? Now, to get the subtraction, like alpha minus beta, we can use the property that we did with even and odd functions. So I'll just put up here, recall that tangent of a negative value is the same thing as negative tangent of that angle, okay? So let's use that to derive the identity tangent of alpha minus beta. All right, so we're gonna use that to figure it out, which isn't bad. I mean, could you go through the whole process with sine alpha minus beta, cosine minus beta, and do this? Yes, you could. A little lengthy, so we're gonna use some properties to cut that down quite considerably. So I could rewrite this as tangent of alpha minus negative beta, okay? Equals, this will be tangent of alpha plus tangent of negative beta over 1 minus tangent of alpha, tangent of negative beta. So what I did, I'll just draw your attention to it. So I took this guy right here, and I kept alpha the same, but I made it a negative beta, which allows me to make it these guys subtracted. So now we just gotta simplify the negative betas. Because we know a negative angle just puts the negative on the outside of it, this is now gonna be equal to tangent of alpha minus tangent of beta over 1 plus tangent of alpha, tangent of beta. So all it essentially did, okay, if you look at these two formulas and compare, it just switched the signs. Pretty much. That's it. So those are our sum and difference identities for tangent. Okay, questions? Now we're just going to use them. So let's do that. Oh no. I used the wrong color. Looks like I've just murdered my whiteboard. have one? No. That's something I gotta buy here. All right, we're not using that color anymore. So example, find the exact value of tangent 11 pi over 12. And one of the examples we did yesterday, that process I'm going to follow for tangent as well. So I'm going to break up 11 pi over 12 into two angles that add to give me that, but also give me those special angles that's on the unit circle, okay? So a little bit of groundwork here. So I can take 11 pi over 12 and split it up as 8 pi over 12 and 3 pi over 12, okay? Now again, these two, I mean, there's nothing special in the unit circle about them, but when I reduce it, I get 2 pi over 3 and pi over 4, and those are on my unit circle. So that's going to allow me to now evaluate this guy, okay? So again, when you first split it up, it doesn't look like it until you reduce. Now, if you split it up and it doesn't reduce to something like this, well, that's okay. Just go back to the drawing board. Maybe pick two other numbers that add to it. Okay, so let's use it. So we have tangent of 2 pi over 3. It's pi over 4. And it's still on the board, which is nice. I'm just going to plug those values into there and simplify. So this is going to be tangent of 2 pi over 3 plus tangent of pi over 4 all over 1 minus tangent 2 pi over 3 times tangent of pi over 4. As you're practicing this yourself, I'd have the formulas next to you, okay? Don't worry about memorizing it right now. Because like I said, actually I still gotta do that. I gotta write myself a note. I gotta contact them and see what's on your reference paper, but I'm pretty sure these are on there. Okay, so let's find each one. So 2 pi over 3, that's in quadrant 2, so tangent's negative there. So this becomes negative square root of 3. Pi over 4 is just a 1. On the bottom, we get 1 minus a negative square root of 3 times 1. So just knowing unit circle values, that makes this even easier. And what I'm going to do, typically we don't write stuff like this. I know you've probably seen it already with my answer key with some things. We'll just flip it around to do 1 minus square root of 3. And the bottom becomes 1 plus square root of 3. And there we go. We just found the exact value for tangent of pi over 12. Now again, could you type in the calculator? Absolutely. But this is allowing us to not have to use that method. We can actually figure it out for ourselves. And the exact value is a lot better to work with than a rounded value. Because if I use a rounded value in a future calculation, then that future calculation is not going to be quite exact. So that's a lot better for us. Okay, so now we're just going to verify identities, and we're done. Now that we got these two formulas, I hate to, well, oh well. We're erasing it. Decisions were made. It's gone. Yeah, it's a shame. I do like that color red too. It's just my whiteboard does not like it. Okay. So now, let's verify the identity. Sine of theta plus 2 pi equals sine of theta. I made the statement when we were graphing sines and cosines that they're periodic, that after every 2 pi, the values repeat. So that's what this is saying. So after 2 pi, you still get the same thing for that. So instead of me just saying it and seeing it visually, can we prove it algebraically? And that's what we're going to do, okay? So that's the only thing. We know this is true already, but can we prove it using what we just did here? So verifying, we pick a side. We're going to pick the left-hand side because that's the only thing we can work with. The right-hand side's already simplified. So we have sine of theta plus 2 pi. So So we're going to use the sum formula, which is written over there for us. So this is going to be sine of theta, cosine of 2 pi, plus cosine of theta, sine of 2 pi. Okay, so again, just using that formula I had boxed over there, just adding those together. And this is nice. What's cosine of 2 pi? 1, right? Yeah. So 1, so this is just going to be sine of theta times 1, which is just sine of theta. On the other side, even easier. What's sine of 2 pi? 0. So this is going to be cosine of theta times 0. So we just get sine of theta. Hey, we did it. So that's my right-hand side. So another way, again, visually we can see it does repeat because it keeps going around the unit circle, but now we have an algebraic way to support that. All right, last one. Let's try one more out. So again, verify the identity. I'm writing way too big there. Let's try that again. There we go. Okay, so we're going to verify that identity. Still going to pick a side. Obviously, the left-hand side has much more to work with. And we know that because these guys, I can substitute these formulas in for, right? So let's go ahead and do that. So we have here left-hand side. So cosine of alpha plus beta. Okay, now, just as a review, notice the signs here. So because I'm doing plus, this sign I'm going to use over here is a minus, okay? If I was subtracting these angles with cosine, I would choose the bottom sign, which is a plus, so they alternate. Okay, so just keep that in mind. So in this case, I don't have to worry about that. I am going to subtract and go with the first part. All right, so we get cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. That is that guy. Okay, so I just substituted its values. Now I'm going to do the same thing for this guy. Okay, so this is minus. So if I go to my formula, cosine of alpha minus beta, I'm going to use a plus sign on that side. Okay? So we're going to get plus cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. And take your time. When you're substituting like formulas into a trig identity, make sure you have your signs correct, because that's where most of the issues are going to lie. Things are canceling out. I can see that this guy cancels out with this guy. And I think we're about there. Look at what I have left. Cosine alpha, cosine beta. Cosine alpha, cosine beta. Is that 2 of them? It is. So this is equal to 2 cosine alpha, cosine beta, which, hey, that's the end of the identity. That matches the right-hand side. And that, my friends, is the sum and difference formulas. Using it in like an application type way to prove things, and use it to help, find exact values without using the calculator. Like we can now find those odd values by using some of this information, which is really cool stuff. Okay? Any questions? By the way, it is I've realized this when I was grading papers. It is very amusing that more and more of my students are writing smiley faces, frowning faces on there. I like it. It's pretty cool. Because put it this way, when you have 20 pages of math notes, it's a little bit of a slog, but when you see that at the end, you're like, oh, that made me feel better. Maybe it was worth it, all that work in the end. So here is your practice.